Okay, so now we're getting started with chapter 10, which deals with shapes of molecules. In order to figure out the shape of a molecule, you first have to draw the Lewis structure of the molecule. So whatever you learned in chapter 9, drawing the Lewis structures, S is equal to N minus A, you're going to use that for all the molecules in this chapter. Before we get started with all of the molecules that we're going to introduce in this video, I want to give you a couple of key terms that you have to understand, okay? So first term is the term molecular geometry. So we're going to be determining every molecule's molecular geometry. What is that? That is the shape of a molecule as determined by the relative positions of the atomic nuclei. So where the peripheral atoms are compared to the central atom, that gives you the molecular geometry or the shape. So whenever we talk about shape, we mean molecular geometry. The other term we're going to use is electronic geometry or electron arrangement. This is basically the arrangement of the electron pairs around the central atom. And their arrangement around the central atom, because they repel each other like crazy, that determines where the peripheral atoms are going to be. Because of that repulsion of the electron pairs around the central atom, that helps us figure out the molecular geometry. So the electronic geometry helps us figure out molecular geometry, okay? The theory that we're using to figure all this out is something called VSEPR, V-S-E-P-R. This is an acronym for valence shell electron pair repulsion. This theory predicts the shape of molecules and polyatomic ions by assuming that the electron pairs around a central atom are arranged as far away from each other as possible. Why are they arranged as far away from each other as possible? Because they repel each other, hate each other. So when they repel each other, they force the peripheral atoms to go in specific directions. Okay, so what we're going to do is I'm going to write down a molecule or a polyatomic ion, and then we are going to draw the Lewis structure. I will just go ahead and draw the Lewis structure, but you should be practicing the S is equal to N minus A. So the more you know, you keep practicing it on your own rather than just copying the final Lewis structure from the board, the stronger you will be. Once we draw the Lewis structure, we will determine the electronic geometry or the electron arrangement, and then we will determine the molecular geometry. And let me tell you right now that the molecular geometry or the shape is exactly the same as the electronic geometry if and only if there are no lone pairs around the central atom. If there are lone pairs around the central atom, then the molecular geometry or shape is going to have a different name than the electronic geometry. So this is important to remember. So we're going to figure out the electron arrangement or electronic geometry, the molecular geometry. We're going to also figure out the bond angles, okay, between all of the atoms in the molecule. And then we will figure out if that molecule is polar or non-polar, okay? All right, so let's go ahead and get started. The simplest molecule is what we're going to do is we're going to use carbon dioxide. So we already did the Lewis structure of carbon dioxide in a previous video. CO2 looks like this. Carbon, double bond, oxygen, lone pair. Okay, so this is the proper Lewis structure of carbon dioxide. So the first thing you do is you count how many electron dense areas are around the central atom. And what do I mean by electron dense area? Well, a single bond or a double bond or a triple bond or a lone pair. Each one of these things are considered one area. Okay, so this is considered one area. All right, so we've got a double bond, so this is one, and then another double bond. 1. So we have 2 areas around the central atom. Everybody see what I'm doing here? I don't pay attention to anything around the peripheral atoms. I'm just focused on everything around the central atom, okay? So I've got 2 electron dense areas. Anytime you have 2 electron dense areas, the electronic geometry, e.g., is called linear. Linear. Why? Because anytime you have electron pairs and they repel each other and they're just 2 of them, the best way they can repel each other is to be as far away from each other this way, not this way or this way. This way they'll get close. But if they're repelling each other and they hate each other, just being linear, this is the best way to go. So the electron geometry or electronic geometry or electron arrangement is linear when you have 2 areas, 2 electron dense areas, okay? What about the molecular geometry? Remember how I just told you guys that if you have no lone pairs around the central atom, the molecular geometry is exactly the same as the electron geometry or electronic geometry. So it's also called linear. These are all things you had in intro chem class. Let me just show you what a carbon dioxide molecule looks like. Here we go. Here's the carbon, oxygen, oxygen, double bond, double bond. See how linear it is? It's a very linear molecule, okay? Why? Because these electron pairs repel these electron pairs. And when they repel them and they go in a linear fashion, these peripheral atoms are forced to be in that direction. Carbon dioxide doesn't look like this or like this. It's like this, okay? Far away from each other, okay? All right, what about the bond angle? Well, the oxygen-carbon-oxygen bond angle, anytime you have something linear, the angle is going to be 180 degrees, okay? Now, is this molecule polar or nonpolar? Well, this one specifically is nonpolar. Why is it considered nonpolar? Because it's perfectly symmetrical. Anytime you have the peripheral atoms identical to each other, they're exactly the same. Very symmetrical molecule. No lone pairs, nothing different at all, no charge. This isn't a polyatomic ion. This one specifically is nonpolar. Okay? What if I had something like this? H triple bond. Okay? This hydrogen cyanide, or if you throw it in water, it would be cyanic acid. This is 2 areas also. Can you see that? It's 2 areas. So the electronic geometry is linear. The molecular geometry is also linear. Why is it linear? Because there are no lone pairs around the central atom. The molecular geometry is exactly the same as the electronic geometry. Okay, the angle is also 180 degrees. But can you see that this molecule is not symmetrical? The carbon dioxide perfectly symmetrical, the 2 oxygens on both sides. Like this is a polar covalent bond, yes. Oxygen attracts the electrons more on this side, and then this is also a polar covalent bond. So this side of the molecule is partially negative, this side is partially negative. They cancel each other out. It's like 2 vectors canceling each other out. This one, on the other hand, nitrogen is more electronegative than carbon, so the arrow goes in this direction. Carbon is more electronegative than hydrogen. Remember, this is a very close to being nonpolar covalent bond over here. So this side slightly positive, this side slightly negative. This is a polar molecule. And the main reason it's polar is because it's not symmetrical, okay? These don't cancel out. So this one would be polar. So I just wanted to give you examples of 2 linear molecules. One of them is polar and one is nonpolar. Okay, now let's do the next one. Formaldehyde is CH2O, and formaldehyde's Lewis structure, so let me just write this down, CH2O. Formaldehyde's Lewis structure is this. When you crunch the numbers, this is what it's going to look like. Again, practice S is equal to N minus A. You will see that this is what it's going to look like. All right, so let's go ahead and do the electron arrangement or electronic geometry. Anytime there are three areas, can you see this is one area, two area, three area. Anytime there are three areas, this is called trigonal planar. Trigonal planar. Okay? The molecular geometry or the shape, molecular geometry or the shape is also going to be trigonal planar. Why? Because remember how I told you, molecular geometry is exactly the same as electronic geometry if there are no lone pairs around the central atom. So it's exactly the same. I'm going to redraw it to make it look more like a triangle. So this is actually the way it really looks. Okay? So what do you think the bond angles would be? Actually, let's take a look at it, see what it looks like. Yep, here it is. Here's my formaldehyde. Carbon double bonded to the oxygen and the two hydrogens. Look, it's a nice little triangle. But instead of calling it triangle, we call it trigonal planar. Okay? What do you think the bond angles are? If you take a circle and you divide it into three parts, circle is 360 degrees divided into three parts. So the bond angles are 120 degrees. Okay? Is it polar or non-polar? Well, obviously this is going to be polar because the peripheral atoms are not all the same. If all of the peripheral atoms are the same, that's different. But now there's an oxygen and these two are hydrogens. This is more electronegative than this. So this is partial negative over here, partial positive over here. Two different poles to the molecule. So this is polar. It's a polar molecule. Okay. If I had a molecule like boron trifluoride, this is, remember how boron's octet is 6? This is the way boron trifluoride would look. It's got 3 areas of electron density, so it would be trigonal planar, electron geometry, molecular geometry, also trigonal planar, bond angle also 120. But look, all 3 peripheral atoms exactly the same. So this one would be non-polar. Okay? All right, moving right along. Let's do sulfur dioxide. So SO2. If you crunch the numbers, you will see that it looks like this. And then crunch the numbers, prove it to yourselves. Make sure that you get that. This is an example of resonance. Remember how we said in the previous videos that when you have peripheral atoms that are exactly the same and there's a double bond, it can keep switching from here to here. Okay. How many electron dense areas are there here? Well, here's one area. Here's the second area. And see this lone pair over here? That's the third area. So 3. Anytime we have 3, the electron geometry is trigonal planar. So anytime we have 2, it's linear. Anytime we have 3, it's always trigonal planar. But the molecular geometry here is going to be different. Why? Because we said that if you have a lone pair, the molecular geometry is going to be different than the electronic geometry. All right, so what is it going to be? Well, this is what sulfur dioxide looks like. All right, let's pretend, okay, this is what, we'll pretend this is a sulfur, oxygen, oxygen. So it sort of looks like this. So it's at an angle. Can you see how it's at an angle like this? So the molecular geometry is called bent, or sometimes in some books they call it angular. Either term works. You should know both terms, okay? Bent, angular. It still has 3 electron dense areas, but because this doesn't have an atom up here, like you did with the formaldehyde, it's not a trigonal planar geometry, it's a bent geometry. What is the angle? It's still about the same. It's a little less than 120, but you can just say approximately 120. The reason it's not exactly 120 is that this lone pair repels these guys more than these repel each other. So it sort of pushes it in. So it's a little less than 120. What about polarity? It's not perfectly symmetrical. So this one is polar. Okay, so we're done with 2 areas of electron density and 3 areas of electron density. Next video, we'll go on into 4 and 5 and 6.